Hi everybody, today we are going to be discussing projectile motion. Projectile motion is motion of an object that has both X and Y components. So like if you kick a soccer ball or a football or a golf ball or fire a cannon, we're basically looking at something that's going to have a curve rather than going in a straight line. All right, so how in the world do we deal with projectile motion? Well, before we begin, we should take a look back on things that we already know. So in the last week, we have spent a lot of time talking about different forms of expressing vectors. For example, having Cartesian coordinates of XY coordinates, or polar coordinates, which is r, theta, so the magnitude and the angle. If you need to figure out the x and y components, you would take r cosine theta for the x, r sine theta for the y. Likewise, if you had an x and a y value and you needed the resultant in theta, we could find the resultant by taking the square root of rx squared plus ry squared, and theta would be equal to the inverse tangent of ry over rx. It's been a few days, but we had also learned what we had called the kinematics equations. These were three equations that help us deal with an object that is in motion and at constant acceleration. Our first equation said final velocity is equal to initial velocity plus acceleration times time. That's useful if you don't know a displacement value for how far an object travels. Displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. That's useful if you don't know a final velocity. And then the last kinematics equation was v final squared equals v initial squared plus 2 acceleration times displacement. That is useful if you don't know time. All right, and those three equations are very valid, but so far we had only use them for straight line motion, like a car skidding to a stop or an airplane hitting a runway and coming to a stop. Today, though, we are going to talk about projectile motions that have both X and Y components. And if you look back, these equations have lots of vectors. I mean, really, velocity is a vector, displacement is a vector, acceleration is a vector. So we almost need to merge the rx cosine, or rx equals r cosine theta, ry equals r sine theta with our kinematics equations. Now, some important statements to make. A projectile has both x and y components to its motion, and the x and y components are independent of one another, and therefore they must be treated so. So we have to break them into x and y components. Okay, so I guess I got a little bit ahead of myself, and we should actually go down here for a minute, because let's say that you have a golf ball, and it is hit at an angle of theta and an initial velocity. That velocity is a total initial velocity, but it's actually going to have both an x component to its motion and a y component, which together will keep this object in that nice parabolic arch-like trajectory. So we could say that initial velocity can be broken into an x component, and the x component of that is equal to the initial velocity total times cosine of theta. The initial y component of the motion is equal to VO sine theta. All right, so that's how we begin breaking these into their x and y components. I could go back then and look at my kinematics equations and rewrite them for both the x and the y. So all I did here is specified the x and the y. So this maroon equation, Vfx, so final x velocity is equal to initial x velocity plus the acceleration in the x direction times time. The green equation, the displacement in the x direction is equal to the initial x velocity times time plus 1/2 a acceleration in the x direction times time squared. And then the teal equation, the final x squared equals v initial x squared plus twice the acceleration in the x direction times the displacement in the x direction. All right, and then I went through, and where the x's were, I plugged in y's, because you will also have a set of equations that deal with y components. Now, if you think about it, what would be the acceleration in the y direction? Well, what is the force that causes objects to move up and down? Isn't that just gravity? So anytime that we had an AY, we actually could replace that with G. And we know that the acceleration due to gravity is negative 9.8 meters per second squared. So let's see if I can get this to work. What about if we took that out? We take that out, and now in our equations where those acceleration in the y direction used to be, whoops, that would be helpful if I would change this to my pen. We are now going to write a g, all right, and you could plug in negative 9.8 meters per second squared. Okay, so G. What about acceleration in the x direction? What is it that causes an object to accelerate or decelerate in the x direction? Well, truly, that would be due to air resistance. But air resistance is pretty negligible, pretty tiny compared to the overall pull of gravity or other objects, and it makes the problem pretty complicated. So for our purposes, we are going to say acceleration in the x direction is 0. So anytime that we replace this as 0, so we can go back into our equations now, this a sub x, I'm going to erase it, and we are going to make that 0. So now that whole term drops out. Likewise, whoops, technology here. That's going to be gone, that's going to be gone, and we're just going to replace those with zeros. So we got a 0 there, that term drops out. And then let's fix this one. 0, that term drops out. So if we were going to take those and rewrite them, these are the equations that I would write on your equations sheet for kinematics. The first main equations are how to resolve the initial velocity in total into the x and the y components. So initial x velocity is equal to the total initial velocity times cosine of theta. Initial y velocity is equal to the total initial velocity times sine theta. Now, if we go back to our x direction, let's take a look here. This, because we are disregarding acceleration in the y, or sorry, acceleration in the x direction, we're saying there's no air resistance. This just tells us that the final x velocity is equal to the initial x velocity. So because we're disregarding air resistance, we're essentially saying that this object will start and finish with the same speed in the x direction only. All right, then this next equation becomes important because it says that we can find the range or the displacement in the x direction by taking initial x velocity times the time. So to figure out how far an object travels in the x direction, all you need to know is how fast it was going and how long it was in the air. This equation right here, VFX squared equals VOX squared, is basically just a restatement of the first maroon equation up here, VFX equals VOX, so we're not even going to bother to rewrite that. Then the three y equations are going to stay the same. So now we can say VFY equals VOY, so final y velocity equals initial y velocity plus g times t, because that's gravity times time. Don't forget to use the negative value for gravity. Then we could say that the displacement in the y direction is equal to the OY times time plus 1/2 gt squared. Again, use negative 9.8 meters per second squared. And what color do we want to go with here? Maybe we'll go back to our teal. The final equation that's useful here is that the final y velocity squared equals the initial y velocity squared plus twice gravity times the change in height. All right. So these are your new revised kinematics. We should put kinematics for projectiles specifically. So if you want to add that to your equation sheet, I said you should have a sheet of paper where you're keeping all of your important equations. That way you have them to reference for quizzes and tests. That would be great. I am also going to post a set of sample problems that I would like for you to work through at your own pace. If you have any